recall yesterday that we defined viscosity solution. And yesterday we worked on the question of existence and uniqueness. There are a few things I want us to recall. So there is this equation, time-dependent equation or evolution problem. Sorry. Actually, I didn't say, but this problem is Rn times 0 infinity. It has the same kind of rho and stuff like that. The theory for this problem is the same like the theory for this problem. For the this is evolution problem. It's the same like this static problem. Without any term, u plus h of x, the u equal to 0 Rn. Okay, the two problems have the same theories in them. So sometimes I might consider this, sometimes I might consider the other one. I claim that they are the same. And this is a static problem, and I add u here. Remember that I have u here. Or in general, I can put any lambda u with lambda greater than 0. And now I choose lambda equal to 1 for simplicity. The reason why we need to put it here so that we have the equation is monotone in U. This is a very important point because later on, when we have lambda equal to 0, that's some interesting phenomena about the cell aggregate problem. And then here we come to that, like we said, so we have the same theory. And then now let me state the definition of viscosity solution again. Let me call this one C, stands for Cauchy problem, and let's say, well, it's not a good name, but let's say S stands for static problem. So definition of viscosity solution for S. So one. Okay, you can deal with semi-continuities, stuff like that, but I'm just going to fix myself with continuous function. So U in the class of C are n, continuous function in Rn, and let's say U is bounded. This can be proved, but let's say U is bounded. So assume that U is this, and we say that U is a viscosity subsolution if for any class function free. Okay, I didn't say, but we can actually assume that this is in C1 Rn, or it can be in C K Rn for any K. And if I have U minus 3 as a shrink maximum at x0. Okay, so yesterday afternoon, actually we did some exercises, and one of the exercises for some of us was that this strict maximum assumption can be removed. So it's equivalent to say that it has a local plus at x0, this is set. Then I have u of x0 plus h of x d3 x0 less than equal to 0. Okay? So you see, I don't replace u by 3 because u is fine. There's no problem with u, but there are only problems with the derivatives, the second derivative, and so on and so forth. So I keep u. But for anything that I need to require the differentiation, I replace it with the test function. And then one more question yesterday I received was that, okay, does it make sense? Use only continuous function, right? It's not differentiable or anything. Well, this is just a symbolic way of writing, right? I mean, this doesn't have any sense because u is not differentiable. But this is what I mean because u is not differentiable. But if I do it with test function, then this makes sense. Okay. So this is just a symbol. What symbol? It's not. It's not equality form. This is so that's why it's interesting. Okay, okay, u minus u is a viscosity super solution. If for all three in C1, u minus 3 has a shrink mean at x0, then I have u x0 plus h of x0, u3 of x0, greater than equal to 0, and so on and so forth. Okay, and one more remark, I figured out that some of you haven't seen this thing, and I did it pretty much quickly. And then one remark was that about constants. C in PD in general. Because you see that there are so many C's in PD, so that's a conventional way of writing. Because so C can change line by line. Instead of using cumbersome notation C1, C2, C3, you keep sort of having a lot of constant. We often the case only use one constant, and it changes line by line.
Can you say C for C?
Yeah. So for me, I told my undergrad student at Chicago, I said, I don't care. C times C is equal to C. You do anything, any computation, ask me, my answer is C. 10% is C, and anything is C. So that's a great point. Okay. So for me now, I don't need to do computation. Everything is C. So this is a conventional way, right? Instead of using a lot of numbers. So that's why you can see that example yesterday I did like u trigger minus u is less than equal to C, and I have xp minus p1 minus h, xp2 less than equal to C, p1 minus p2, and so on. And so those C's are different, but like conventional way. Let's say this. You can take maximum of anything like that. Okay. And then one more review was that yesterday we do uniqueness proof. That's a big thing. For first order Hamilton-Jacobi equation. This was derived by Crandall and Lyons by a clever way of using doubling variable. Because u and u tutor are only continuous in general. They are not, we don't assume anything like, in general, u and u tutor are even only semi-continuous. That's something different. And the idea was from Kruskal's, but I should say a little bit clearly that in Kruskal's argument, the idea was very different. So Crandall and Lyons took the intuition and then they sort of worked on it. And then nowadays in viscosity solution, this is a very, for example, if I work, we have an exercise that today you can do that, but it's something like you're always going to do some doubling variable. Just double the variable and put some constraint stuff. Sometimes people can replace it by different things. And then you put whatever you need. For example, yesterday there were some terms because you need to bound T and S and some other terms, so just do whatever you need. Like use your common sense and do whatever you need. Okay, but this proof doesn't work for second order Hamilton-Jacobi equation. I'm not doing that, but for second order, Hamilton-Jacobi equation of the form as a ut plus h of x du d squared u equal to 0. This proof doesn't work because here we require much more derivative. The proof of Crandall only also came in the early 1980s. And then there was a special case that Pierre Louis Lyon got it, but it was not the general case. The first general proof by using a very clever idea of using soup and in convolution in order to overcome the difficulty was given by Bob Zensen. So Zensen got the first proof by using soup and in convolution for uniqueness. And then Ishii has an easy lemma that have the general proof. So this requires C01 regularity and some other assumptions. So this is for continuous subsolution, continuous discursive solution. So there are two famous lemma. Either Zensen's lemma by Bob Zensen, or PC. Sometimes people call it PC's lemma, or sometimes people call it Crandall EC lemma. I don't know why, I don't know. But there is to handle the second order case. I'm not going to do that, but I want to mention. And the second order case actually is hard, it's not easy. And then there's a very famous paper by Crandall, EC, Lyon's, like user guide to user guide. This is a very weird title. Of viscosity solution, this is cited a lot in the literature. And how it comes on Google Scholar. I think the reason why Google cite is kind of like, it's basically unreadable, but just cite it because it contains